Hi, this is Professor Jemai Chen at California State University, Long Beach. In this video lesson today, we'll look at Slant asymptotes for rational functions. A rational function whose degree of the numerator is greater than the degree of the denominator function is likely to have a Slant asymptote. In such case, we use the long division algorithm to express the rational function in the form of r of x equals the quotient q of x plus the remainder r of x divided by the divisor polynomial d of x. The division algorithm guarantees that the degree of the remainder polynomial is always less than the degree of the divisor polynomial, which means that as x goes to infinity, this expression would eventually go to 0. Because the denominator polynomial dominates over the remainder polynomial on top, which means over time as x grows larger, this expression gets to be smaller, eventually goes to 0. What this means is that as x goes to positive or negative infinity, the rational function r of x approaches the quotient function q of x. This q of x function is called the Slant asymptote. It's also known as the Oblique Asymptote, and the reason why it's called a Slant asymptote is because it's neither a horizontal line or a vertical line. It's given by some function. This q of x could be any function, could be a linear polynomial, could be a quadratic polynomial, could be even a higher degree polynomial, we don't know. That's why it's typically a curve instead of a straight line, horizontal or vertical line. Let's look at an example next. In this example, let's sketch the function r of x, whose numerator polynomial is degree 2 and the denominator polynomial is of degree 1. It satisfies the condition that the degree of the numerator is greater than the degree of the denominator. First step of sketching a rational function is always to factor the numerator and the denominator. In this case, the denominator is already in its reduced most factored form, so we just have to worry about the top. We have factors 1 and -5. Which gives us x plus 1 times x minus 5, all divided by the x minus 3. Next, we find the x and y-intercepts. For the x-intercepts, we set the rational function to 0, and recall that the rational function can only be equal to 0 if the numerator function is equal to 0, which means we're going to set this top portion equal to 0, and that means x has to be -1 or 5. For the y-intercept, that's when we set the x value equal to 0. So if we go back to the original rational function r of x here, and simply just replace all x with 0, then we're left with the constant coefficient, which is -5 over -3, which reduces down to positive 5 over 3. Next, we find the vertical asymptotes and the behavior near the asymptotes. We find the vertical asymptote by setting the denominator function equal to 0. In this case, that's x equals 3. To figure out the behavior around the vertical asymptote, we pick test points to the left and to the right of the vertical asymptotes. In this case, I'm going to pick 2.9 and 3.1. It's easier to use the factor form of the rational function when we're checking for the signs on the test points. When I use the test point of 2.9 back in the original rational function, I would get a plus sign for the first factor and a minus sign for the second factor over the minus sign on the denominator, which gives me an overall of a plus sign. This means that the y value goes to the positive infinity as x value approaches 3 from the left, which means that near the asymptote the function should have such behavior. For the test point 3.1, I would get a plus on the first factor, a minus on the second factor, over a plus on the bottom factor. Overall gives me a negative sign, which means that the y value goes to the negative infinity as x approaches 3 from the right. This then gives me a behavior going downward as I approach 3 from the right. In step 4, we find the horizontal asymptote. But notice that the degree of the numerator is greater than the degree of the denominator, and that is why there is no horizontal asymptote. And this is also why we actually have a Slant asymptote instead. So in the next step, we're going to find the Slant asymptote through the division process. You can do the division using the long division with the polynomials, or the synthetic division in this case because we actually have a factor of x minus 3 on the bottom. You can use the number c equals 3 in a synthetic division process. Here I'm going to illustrate with the long division. My first term in the quotient would be x to match up with the x squared in the dividend, and then I have minus 3x as my second term. When I subtract those two things, I have a minus 1x left. I need to carry one term down to match the number of terms in my divisor, and then I need a minus 1 on top to match up with the first term of the new dividend, and that gives me a plus 3 That's the constant term. When I subtract those two things, I get minus 5, minus 3, and this gives me a remainder of negative 8. That means I can write my original r of x function as x minus 1 as the quotient, plus the remainder, that's negative 8, over the divisor x minus 3. And remember, this quotient function is the slant asymptote. Finally, we're ready to sketch. You might need to plot additional points just to make sure your graph is smooth. Once you lay down your axes, my first action is always to identify the location of the vertical asymptotes and horizontal asymptote. In this case, it would be the slant asymptote. A slant asymptote is y equals x minus 1, which means that it has the y-intercept at negative 1 with a slope of 1. So to do that, I'm going to start with negative 1, and the slope being 1, that means I can go up 1 unit and then right 1 unit to identify my next point. This gives me 2 points, so then I can connect those 2 points and make a straight line out of it. Next, I'm going to remind myself the behavior around the vertical asymptote. The function is going to go to the positive infinity as I approach 3 from the left, and the function is going to go to the negative infinity as I approach 3 from the right. Next, I'm going to label all the points that the function crosses through. For example, the x-intercepts are at negative 1 and 5, so that means the function needs to go through this point 5, also needs to go through the point negative 1. The function has y-intercept at 5 over 3, well that's about 1.67. I think I'm about ready to sketch this graph. I'm going to start from the right hand side here. I need to draw a curve that gets really close to the slant asymptote and then cross the point 5 and eventually goes down like that. On the left hand side, I need to have a curve that gets really close to the slant asymptote as I go up, crosses through the point negative 1, and then come up to cross the point 5 over 3, eventually grows along the vertical asymptote to the positive infinity. This might not be the best accurate drawing in the world, because the scale is a little bit off. That's why it's called a sketch. You could verify with your calculator or any other computer software just to see that if the general behavior is the same.